mechanical engineering at the University of Nevada in Las Vegas. He then came to the University of Calgary in 2015 for his PhD in biomedical engineering, supervised by John Bertram and James Croft. He's currently a postdoc in Art Quo's lab, but will be starting an assistant professor position at Brock University in July. So his research interests include very broadly biomechanics, neuromechanics, gate-assisted technologies, and locomotion energetics. Today, he'll be presenting some of his recent work, pursuing the objective in a discrete walking task.
Thanks so much. I was hoping I'd have the chance to annoy Michael a little bit. I have sort of cheated and I have 2 titles, but I guess he's not here today. So some of you might have seen me walking around the halls, or maybe not me, but maybe you noticed a little toy car that I was controlling with a remote control. So that's what I'm going to talk about today, is what the heck I was up to. So I spent a lot of time and energy in pursuit of this radio-controlled car last year. And this talk is about what I learned about human walking in that process. And then here was the advertised title. So I did throw a couple of the vegetables into that one. They were just kind of hidden. Humans minimize time and energy during a locomotor pursuit task. I'll begin by just noting that something we do all the time is we catch moving targets, right? So sports is an obvious example. You run to catch a ball, or even you position the bat so that it catches up to the ball as the pitcher throws it to you. Or maybe you're actually catching up to another athlete, right? You're running after them. This seems to be a skill set that we actually practice pretty early on in life. So this is my 14-month-old son chasing after a crawling robotic crab toy. I'll just get a little bit more precise in what I mean here. So in a pursuit task, you intercept a moving target that's either approaching you or moving away from you, and typically in sort of one line, so like a one-dimensional type of a thing. And one question you might ask is, what makes a successful pursuit strategy beyond just the fact that, okay, you actually caught up to the thing? How might you go about that? How might people go about that? But before I go there, I'd like to note, and I don't know why this video keeps coming up dark. There we go. So I'd just like to note that, the juxtaposition between a walking or a locomotion task like this and the type of studies that we often do in our labs, right? We bring people in, have them walk on a treadmill, do some motion capture, maybe some ground reaction forces, but steady walking at a constant speed most often, right? It's very different. No accelerations, no transients. This is a discrete task, right? You have a start and an end to the task. So I just think that makes things a little bit tricky, because a lot of the analysis that we typically do for steady gait doesn't necessarily translate to this task. So an easy example is the cost of transport, where we measure the metabolic energy a person consumes while they walk, for example, on a treadmill, divided by the distance, the unit distance traveled. So if we do that for a range of steady walking speeds, we can create this nice bowl-shaped curve, where the minimum of that curve aligns nicely with typical speeds that we see people preferring to walk at, again, in steady gait. And so this is the problem. Cost of transport tells you what happens in steady gait. It doesn't tell you much about what a speed trajectory might look like in non-steady walking. And I actually think this is a pretty big problem, because ecologically, we're not walking around every day on a treadmill, right? We're walking around corners, we're speeding up, we're slowing down, we're walking upstairs. So I think this is actually a bit of a problem that we should be working toward addressing in the field. Now, people have proposed certain kinematic strategies to deal with this problem of interception or pursuit. So in this example, we're looking at now a two-dimensional interception task, but it's the same basic idea. The chaser is chasing after the target, of course, and the target is moving along its trajectory. And the basic idea here is that so long as your bearing angle with respect to the target is held constant, you'll eventually catch up to that target and have a successful pursuit. But in a one-dimensional pursuit task, this doesn't really help as much, because the bearing is always 0. So it just kind of doesn't really tell you anything. The only thing you need to know is that your chaser speed needs to be faster than the target speed, but this is more or less trivial. Another example of one of these kinematic strategies we've seen people use is the idea of how do you catch a baseball? Let's say you're an outfielder, the ball's flying through the air in a parabolic trajectory. Do you run forward? Do you run back? How do you figure out which way to go and intercept that moving ball? Well, the general idea here is that if you're running forward, running toward it, or moving back, so long as you make the time derivative of tangent of the elevation angle constant, you'll eventually catch the ball. Now, it's a little bit abstract, but the basic idea is that this angle should change in time linearly. But again, this is still problematic, at least for our purposes, because it only applies to ballistics. This relationship only works out assuming that your moving target is under the acceleration of gravity. Some more problems with this approach to the problem. None of these approaches include gate mechanics or energetics. And we think that these are actually really important things that inform our gait and our locomotion. It also neglects transients. So for example, in the constant bearing example, oftentimes you'll hear the folks who do this research say something like, well, this bearing angle kind of changes in the beginning and the end, but in the middle, there's a nice constant bearing angle, so we don't really care about it. They kind of just shoo it under the rug. But it could be that these things are important, right? So think just simply things like acceleration. You might want to understand the acceleration profile that a person uses to catch up with a target. And interestingly, you also can't predict speeds. Even though you might expect, if you know the angle of pursuit, and that's constant, then you'd expect a constant speed to catch up with that target. But just because it's constant, that doesn't tell you what the actual constant is. So you still don't even know what speed a person should use to approach. And you don't know accelerations, even though the whole idea here is we're using a kinematic strategy to describe this. So there's just a lot of limitations with this approach. Well, in lieu of a good strategy that we've seen in previous work, let's just imagine what you could do, okay? So you have a chaser and you have a moving target. That target has some start distance and it has some velocity. And let's just assume that the velocity of the target is a constant in time. So it's just a horizontal line in time. And that means that its position is always increasing also as a line in time. So you walk towards the target, you catch up. We call this interception once you catch up to it. Let's just naively say, even though I told you cost of transport can't predict a speed trajectory, let's just naively say, what if you just walked at that one speed the whole time? So that could be a trajectory, right? And then you would just have a flat speed profile like that. The only stipulation being, of course, that whatever that speed is, it would have to be at least greater than the speed of the target. There would be some energy costs associated with this speed profile and some time duration associated with it as well. We can imagine a totally different profile. So how about constant acceleration, constant deceleration, this sort of triangular looking thing. And let's say you do this with generally on average higher speeds. So maybe there's a larger energetic cost because you're walking at faster speeds, but there's a shorter time duration. You could also imagine something in between those two, this sort of rounded shape, whereby you have an intermediate energetic cost and an intermediate time duration. The point is we could keep doing this exercise and we'd quickly realize you can come up with any number of arbitrary trajectories that might work, right? But that doesn't help us understand what humans do or what humans should do or what might be optimal. So the objective of this study is more or less to develop a model that utilizes mechanics and energetics to predict and understand optimal speed trajectories during pursuit. Now, how are we going to do that? First, I'm going to talk a little bit about some optimal control approaches to modeling discrete walking and also some experimental methods that we used. Then I'm going to talk a little bit about some of the predictions we can make with this model. So for example, how things vary with target speed or the target start distance, or if we take the prediction to the total extreme, how much can we predict with using just a single data point? And then I'm going to talk a little bit about some of the insights that we got from this study. What are the things that we learned in the process? So this idea of coasting, I'll talk a little bit about what that is later. The fact that people might walk towards an approaching target, time valuation being an individualized characteristic of an individual. And then I'll talk a little bit more about cost of transport in the context of this study. So we'll start with optimal control. This was some previous work that was done by Elizabeth Carlisle. She was in our lab just recently, took off. But basically she did an experiment where she asked someone to stand still and then walk a certain distance forward, come to rest, and then turn back and do it again. Very simple task. They used a simple inverted pendulum model to model this process with a point mass for the body and massless legs. And they utilized push-off impulse from the trailing leg. This was the control variable of our optimization. And collision losses in the forward leg determined by the dynamics of the inverted pendulum. The objective of the optimization was to minimize costs for energy and time. Energy being a summation of all the push-off work done in each of the steps of the walk, and a linear time cost. So just the time duration times a coefficient scaling that cost. The decision variables in the model were, as I said, push-off was the control variable. So the optimization got to decide how strong of a push-off to have with each step, and resulting speed trajectories, as well as time duration. Again, the distance traveled was fixed, and so this was essentially the independent variable in the experiment. If we look at speed profile, so speed versus time, this is an example that they found for a short walking bout. And as they asked people to walk longer and longer distances, the profiles morphed in that sort of a way, which matched reasonably well with what humans did. So sorry, I didn't explicitly say this was their model outputs and these were some average human data. And then another thing you might observe is that the longer you walk, the more time you spend near some sort of steady or quasi-steady speed, right? And so this speed could approximately align with cost of transport depending on how this parameter was tuned. So speaking of tuning that parameter, what happens when we increase this coefficient in front of the time cost? Well, speed profiles increase in magnitude. So people are walking more quickly, or rather the model is walking more quickly, and duration is decreased because speed is increased. So we think of this coefficient as being a sort of evaluation of time. How much do you care about reducing this time cost relative to how much energy you consume? So I applied a very similar model to a pursuit task, but with some important differences. Obviously, it's a different task. So of course, one of the main differences is the ending of the task depends on when you actually catch up to the moving target. It's no longer walking a fixed distance. And so as a result, we have all the same old decision variables. Push off is again the control variable, speed trajectories, time duration, but now we have a new one, distance traveled as well. So that is something that the optimization can decide based on the speed profile it chooses. Here's an example of a speed profile we get for a target that's moving away from you. So step speed versus time. You might notice it actually doesn't look all that different from some of the other profiles we just looked at. But now we're stopping at interception. So we stop a little bit earlier. We don't fully come to rest. As I said, we also had push off. And what we find is if we look at the push-off work per step over time, we find that push-off impulses are more work intensive early on. And that's partly just because not only does the push-off work have to overcome collision losses, but it also needs to accelerate your body forward and increase speed. It sort of approaches some sort of quasi-steady push-off work toward the middle of the walking bout, and then kind of trails off toward the end. And then we can also look at collision loss, which is sort of looks like a mirror image of push-off work, right? So collision losses are relatively modest early on, and that's because speeds are relatively low. And then they also sort of approach a quasi-steady, trade-off with push-off. And then they kind of increase at the end as you come to a stop. The area under the push-off curve is essentially our energetic cost in the model. And one thing we might notice is if you begin at rest and you end at rest, the areas under both of these curves should be equal to one another. We can also put metrics to characterize these speed profiles. So for example, just the average speed of that walking bout, the time duration from 0 to interception, and the distance traveled over that same time. We can also look at energy time trade-offs. So we're plotting cost as a function of time duration. And I already said that time was just a linear cost with time duration. So it's just proportional to that duration. But then energy cost rapidly decreases. And the reason is because at larger durations, you're walking at slower speeds, and therefore you have much smaller push-offs. And so it has less energy associated with it. You add these two together, you get the total cost in the model. Let's say you wanted to walk really fast. You have a sort of a tall, skinny speed profile. And you can see there's a lot of push-off work there because you're walking at very high speeds. If you walked more slowly, you'd have sort of a stout, wide speed profile with relatively little push-off work and larger time duration. And of course, the optimum is somewhere in the middle where these sort of trade-offs kind of balance off. So when we did experiments, we decided to do some of these experiments in the hallway leading up to the oval. And that's just because we'd have a nice long hallway where we could walk a good distance if we needed to. We did examples with a fleeing target, which I'll call a positive velocity, by the way. So it's basically just a radio car is moving away from the subject, and they're standing still until the car passes a certain time point. They're given a cue to start walking. They catch up to the car, just lightly touch the netting and come to a stop. Turn around, come back, wait for the next one. We also did this with a still target. So the car is basically just sitting there and the person is walking up to it. By the way, if you're curious, yes, this is a butterfly net, and it was very helpful. We also did with approaching target. So now the car is just simply moving toward the person, but other than that, the experiment is more or less the same. We used 3 fleeing target speeds, 1 still speed, so that's just 0, and 3 approaching target speeds for a total of 7 target speeds. We tested 4 target start distances, ranging from 2.5 to 10 meters far away from the person. So a total of 28 target conditions, 2 repetitions each for a total of 56 total trials per subject, 10 subjects recruited for the study. We also placed IMUs at the feet of the individual to measure accelerations and calculate step speed, step length, and step time, ultimately to calculate average speed, distance traveled, and time duration. And we placed IMUs at the wheels of the car to measure rotational frequencies and thus the speed of the car moving forward. Okay, so I'll talk a little bit about some of the predictions our model could make, both with varying target speed and target start distance. So to begin with, I'll just show a speed profile that the model says is optimal when you're approaching a still target. So this purple one over here, this is step speed over time. For a blue target, which is an approaching target, and that just as a reminder, approaching means it's a negative speed, still means it's a 0 speed, and then fleeing means it's a positive speed moving away from you. So some of the predictions we could make is that average speed as a function of target speed actually increases as the target is moving first towards you and then moving away from you. You walk faster and faster. And just to show you what we're plotting here, the individual data points are sort of discrete optimizations with our model at those parameters selected, whereas the curve underneath it is sort of a smooth approximation of our model, just to kind of help see the trends. The time duration was also predicted to increase as you chase after targets moving away from you. And distance traveled also increased. So we can compare these predictions with human data. By the way, all these predictions are for the 7 target speeds, but only for a single target start distance so far. So here are some speed profiles that people did. The colored curves are what individuals did per each of the 7 target speeds. And the dark line is the median individual. And then we have speed versus target speed again, but now for the median subject, the line is just a linear interpolation. And then we have shaded regions representing quartiles of the distribution of the data. So the inner shaded region is 25 to 75% quartiles. The outer region is basically the entire range of the data from 0 to 100. Also with duration and distance traveled. And so if you just kind of squint your eyes, we can say, well, qualitatively at least, the model predictions kind of do something pretty similar to what the empirical data is doing. Now, what I'm going to do is I'm going to take this column, and in the next slide, it's going to kind of just rotate so that we'll have 2 rows instead, just to fit it on the slide a little bit better. Okay, so in the top row, we're looking at the same empirical data we were just looking at. In the bottom row, we have the model data now in these gray curves. And now let's look at what happens when we vary target start distance. So from blue to red, there's increasing start distance. So blue is with a 2.5 meter distance, and red is with a 10 meter distance. And similar in the model, from dark to light gray, we go from close by to far away. And what we find is that basically all 3 metrics, average speed, duration, and distance, all increase with target start distance. We can take a closer look at comparing these 2 things. And if we wanted to sort of focus in on where does the model not do as good of a job at making predictions, it's basically right in this region here where we have a very positive target speed. So that means the target is moving away from you very quickly. And what we find is that the model wants to keep increasing its speed more and more and more, up to 2.5 meters per second in this example. But basically humans are kind of topping out at their upper limit. At least that's our interpretation, is that we think that people are just unable to walk faster or unwilling. And so this has an effect on time duration and target distance, of course, as well. But despite that, the model still explains anywhere from 63 to 92% of variance in the empirical data when we draw a linear regression between the model and the human data. So 0.92 for average speed, 0.63 for time duration, and 0.89 for distance traveled. Okay, let's take this prediction game to the absolute extreme. What can we do with a single data point? I put the objective function up there again just as a reminder. So we're minimizing a combination of energy and a linear time cost. So here's what we do. We kind of like the experiment I explained earlier. We ask the subject, start here, walk 5 meters, come to a stop, and then we measure the time duration it takes for them to do that. For this subject, their time duration was 5.1 seconds. Doesn't really matter, but that was the number. So that's the single data point that I'm referring to, is that one measurement. From there, we determine that individual subject's time valuation, what their parameter is that can match this time duration given this task. And then we make basically all of the predictions. So we predict speed profiles, average speed, duration, distance, for all 7 target speeds, and for all 4 target start distances. So we make basically every prediction we can, every one we've shown, and then we compare them all to the human data. And it still does a pretty reasonable job of making these predictions. So R squared of 0.87 for the shape of the speed profile, R squared of 0.92 for average speed, 0.78 for time duration, and 0.95 for distance. So even just with that one data point, we can still actually predict 503 data points for all of these conditions. And of course, if we can do this on one subject, we can do this on all subjects. And so we show the distribution of R squareds there per each metric. And they all do reasonably well. Okay, let's talk a little bit about some of the insights we got from this study. One thing I'll point out is that, so these are the speed profiles I showed before for the model on the left and humans on the right, is that speed kind of drops off just before the person intercepts the moving target. And we call this coasting, basically. So what I've done here is I've plotted out for all 28 conditions, just the last 6 non-dimensional seconds before leading up to interception for all of the 28 conditions. And what we see kind of the systematic dropping of speed over that time period. And we also see it in the average human subject. And so we can analyze what's going on here. We can make a comparison. What happens when you have a coasting solution, like the type that the model predicts being optimal, and we compare that to a non-coasting solution? For example, what cost of transport might predict is that you should walk at the same speed constantly. Well, when we make that comparison, we find that energy cost decreases by 10.5% when you coast. Time cost goes up a little bit by 4%, and total cost still goes down by 2.3%. So that's why it's optimal. And the basic idea here is that toward the end, when you're about to intercept, you can stop pushing off as hard, save a lot of energy. Now your speed will start to drop as well, which means that your time is going to increase as well. But it takes too long for you to lose that momentum such that you'll gain more advantage out of saving that energy than you do losing the time. Another thing we saw that we thought was interesting is why people walk towards an approaching target. If the target's coming towards you, you can just simply stand there and wait for it to come towards you. So to understand this, I'll plot cost versus time duration. As before, time is a linear cost with duration. Energy cost drastically reduces over that duration, and the total is the sum of the two. And then what happens if we decrease this time valuation parameter? So of course, energy doesn't change, but time is now a shallower slope. And we can do it again. And we can do it again until time cost is actually 0. Now, the optimal strategy is one that would follow along the minimums of these black curves. And the just stand and wait strategy sort of intersects with that optimum at the time duration it takes for the car to come meet you with you not moving towards it. So basically this happens when you have 0 time cost. So in other words, it only makes sense to just stand and wait if you have no valuation of time. And sure enough, we mostly saw people walking towards the target. Now, when giving instructions for the experiment, subjects were, I told subjects basically they could choose just to stand there if the target was approaching them, or they could walk towards it. So they knew they at least had the option. We did see a couple of examples of subjects not taking, for example, a large enough step to register in the IMUs, or sometimes they wouldn't move their feet at all, but maybe they'd lean forward and reach toward the thing. But in general, and on average, we found that speed was non-zero and that people were approaching the target, even though they didn't have to. So time valuation explains data better than aggregate. I'm going to put a lot of data up here. You don't need to really follow along all the details of exactly what it's showing, but I'll explain to you kind of what we did. So the aggregate time valuation, all of these data points represent all 28 conditions for all 10 subjects. And then we have 4 curves here. Each of those 4 curves are coming from the model based off of a single time valuation. So the time coefficient in front of the time cost is basically tuned to match the aggregate of all these data. And then also for time duration and distance traveled versus target speed. But then what we did is we compared that to a slightly different process where now instead of having 4 curves matching what the aggregate data did, basically we gave each subject a set of their own 4 curves. So each color represents a different subject, and they should have 4 curves that correspond to their 28 data points. Again, for average speed, duration, and distance is a function of target speed. And then what we do is we evaluate the root mean square error between model and human. And we find that when we look at the individual time valuation version of things, error is reduced by about 3% for average speed, 38% for time duration, 39% for distance travel. And so basically the idea here is that individuals have their own distinct valuation of time. Now you might be saying, well, we went from 1 parameter to 10 parameters to describe all of our data. Of course, things get better, but they don't have to get better, right? They could just stay the same. And so basically what we're showing is that by giving each individual their own time valuation, we're explaining a little bit more of the variance in our data. So in particular, our inter-subject variance. And so we think of this parameter as being something specific to an individual. right? Some people walk faster, some people walk more slowly, some people skip up the stairs, some people, toddle on their phone or something, right? Okay, we'll talk a little bit about cost of transport again. So this is kind of how I think about it. Cost of transport still works, but it works for a subset of short walking bouts, right? For example, we talked about this. If you walk at longer and longer distances, the limiting case of that could be thought of as cost of transport, right? What happens when you're doing steady walking for, and effectively, there's no endpoint, right? You're just walking. And then short walking bouts, we can also think of as being a subset of a pursuit task. It's just simply that you're intercepting a still target, right? And then pursuit is a dynamic walking task that includes short bout walking and cost of transport walking. And so with our model, we're sort of like able to predict all these different things in some sort of unified way. Okay, I'm going to tell you a little secret, and that's that I actually don't care about pursuit all that much. It's actually not that interesting to me. But I think the thing that is interesting is this energy plus time model. One thing we can do, by the way, is we can do this interception task in 2D. And so we've done this and it's working well, but we're kind of still in the process of analyzing it. But we can also explain a lot of other things like more ecological locomotion, I think. So I'll give a nice classic example, the pace of life, Bornstein, 1976, Nature. So they find this really nice, clear relationship between walking speed of pedestrians on a sidewalk to the population of the city that they live in. So, the idea being that people in big cities might walk faster. Well, people have suggested all kinds of different ideas for why that might be. One way to think of it is in terms of your valuation of time. Are people in bigger cities more busy? Does their time mean more to them? People in rural areas, maybe they care less about their time. It's one way to think about the problem. And then we also think that the nice part about energy plus time is it doesn't just have to be a locomotion model. We can model all kinds of different movement tasks within this paradigm. So for example, Jeremy did his HPL talk a couple of months ago and talked about a very similar model applied to a reaching task. So I think it's the utility of this way of thinking of these trade-offs between energy and time that could be really powerful and give us a lot of insight. So I'll just summarize what I've talked about today. So we used optimal control to predict pursuit strategies of humans chasing after a radio-controlled car. We found that the model can predict our empirical data reasonably well. So it can predict speed profiles, average speed, time duration, and distance traveled. And we found that speed, duration, and distance all increase with target speed and with target distance. And even that if we just measure a single data point, we can still make reasonable predictions. We learned something about this sort of coasting phenomenon, right? So you can kind of come to a stop right before you're about to intercept. This the example I always think of is if you're in the grocery store and pushing the cart around and you want to stop at that point in the aisle, you kind of just give the cart a little nudge and it coasts to a stop where you're going to, right? We also found that people walk towards an approaching target, even though they don't have to. Time valuation being an individual characteristic of the person. And cost of transport, you could think of it as a subset of shorter walking bouts, which is it's in and of itself a subset of a pursuit task. So with that, I'll just acknowledge all my lab members who helped to make this presentation a lot better and some of our funding sources. And before we go, I'd just like to give my son a few pointers here. I think he's on the right track, but I think he could slow down a little bit when the crab's approaching. He could speed up a little bit when it's leaving him, but he's on the right track, so we're getting there. With that, I'll take any questions you have.
So you said that you have an analysis of 2D.
Mm-hmm.
So I was wondering what you would think or what you would expect in a 2D class. If you think of the two toddlers going toward each other and they're like wobbling, maybe a lateral. Like what would you expect that people walk forward slower and would you add in certain things?
Well, I think in that example, It's less about like modeling, like for example, medial-lateral actions in, let's say, locomotion. It's more about understanding trajectories. So for example, if the car was moving, let's say it's moving away from me, but it's some distance to the side of me as well. Now I have to choose an angle to catch up to it as well, right? So in the case of the kids, they're trying to, it's collaborative, right? So they're trying to come together. In that case, it's really mostly just a pursuit task, right? Because they're probably going to be in a line. Now, if it were a game of tag, it could be a little different, right?
On a similar idea, not so much 2D, but even if it was just a 1D situation.
Yep.
If you had two humans walking together and they want to employ this coasting phenomena, and they both have the same cost function, wouldn't they never reach?
When you say walking together,
Well, they're walking
towards each other. Okay.
Presumably, they want to.
I see.
Connect. If they're trying to coast.
Well, coasting in this context, it's usually never that you decrease speed to come to a stop. Usually, you kind of taper off a little bit, but you continue to walk towards it. And in fact, we don't ever see speeds that drop below the target speed, right? Because then you'd be passing it up and then kind of waiting for it to catch up to you again. So typically, it's just a sort of a more subtle effect that we see.
What happens if your target was also a human and not a robot who was trying to optimize it?
Yeah, and to your point, an original version of this experiment had a person acting the role of the car, but we thought it might be a little more objective if we didn't have a person, because unconsciously, even if you're trying not to, you might try and facilitate the interception as well, right? Maybe you start slowing down to let the person catch up a little bit or something like that.
Just wondering if it becomes like a game theory situation, right? Where
yeah.
Odd solutions for it.
Yeah, perhaps. But I think a good example of it is if someone's, let's say Olivia's coming to give me this remote, right, from across the room. I'm probably not just going to wait here for her to bring it all the way to me. I'm probably going to meet her at least part way, right? I think that's like a nice ecological example of it. And in fact, when we were doing the experiment, I remember it was a very meta moment, because the person who was helping me pilot is actually that person I mentioned, Elizabeth Carlisle. She was acting as the subject, but then we had a marker placed on the ground as the start distance, just when we were piloting things. And she would hand it to me, and she would come and like walk and like give it to me. And it was just this weird moment where I realized the experiment was happening outside of the experiment. It's kind of cool.
That's really interesting to think about, this idea that somebody's bringing you something and you approach them to, and I feel like any normal person does that. Somebody's approaching you with something and you approach them to
right.
That.
Yeah, and I think
thought about that, but there are instances where I've had to go the entire way and somebody doesn't budge at all, and it's not because they have zero valuation of time. It's usually because they're a jerk.
Well,
what's going on there?
it's your negative cost of the satisfaction of thumbing your thumb in someone's eye, right, versus their valuation of time. But so this is an experiment I think would be pretty cool, right? You could do a version of that task where it's not another person, and so you don't care what happens to the target, right? And then compare your speeds or whatever else to if it were a person, right? So what we're measuring here when we think of valuation of time is kind of like a nominal, implicit valuation of time, but then you can also imagine more explicit things, right? So maybe your social cost is you also care about their time cost as much as yours, or maybe it's a fraction as much of yours, right? And then maybe it's you add them together or something and you get that example, right?
Going back to the coasting, what would happen if you didn't have to stop when you intercepted? Like if you kept walking but your speed wasn't, like it doesn't matter how fast you're going, would you still see the coasting?
Yeah, so like if hypothetically you were just supposed to walk forever afterward, I mean, I wouldn't expect to see coasting because I don't think it would make much sense, right? Because then you would just have to get back up to speed unless you were, I mean, theoretically you could be allowed to walk more slowly after that. But in general, we find that, well, yeah, I suppose it could be actually, because yeah, because so I guess it would depend on the parameters of the target. If, let's say, the target's moving really fast away from you, and you have to walk really fast to catch up to it, you probably would coast and then transition to a lower, more comfortable nominal speed after that. So I guess it depends.
Were your subjects allowed to increase their speed to the point where they were jogging or running?
No, we specifically asked them only to walk, mostly just to keep things controlled and a little bit more simple. One of the things I regret is having some of the car speeds that were a little fast, because people really had to, like, sometimes they had to really put on the gas. And, as you saw in some of the curves, that's where things start to get a little.
I think that's really neat and interesting. And of course, it happens right around 2.5, or it happens, or maybe it happened around 2.2, or
Yeah.
close to what you think of as the walk to run transition.
Right.
And there's no ankle in your model,
Right.
or anything like that.
Yeah, so the model can basically hold on to the ground,
yeah.
so it doesn't fly off. So it has this sort of built-in advantage, but it also creates an energy penalty, I believe. But it still seems to be the optimal thing for it to do. So yeah.
When you look at the two bodies that walk towards each other, there is one thing that is interesting, and that is they don't have a collision.
Don't they? I'm trying to think back. Don't they hug?
Yeah, but it's not like running into a wall.
Well, are collisions instantaneous, or are they more like spring damping type things?
Look at that.
Yeah.
No collision whatsoever, and you don't have that in your model. So they do something that you don't look at.
I'm not sure I follow. I don't think there's a collision in my experiment either, unless I'm misunderstanding. They pretty lightly touch the net usually. Also, even if there were a collision, you might just imagine that people care less about hitting, an inanimate object, whereas they might care about hitting their friend. But
if you hit that little flag,
yeah.
that could be a collision.
Oh, sure. I mean, again, it just depends on like how.
This is something completely different, and they have in their plan what they do, something implemented that is, I don't want to have a collision.
Yeah, well, certainly I agree that when the thing you're pursuing is another human being, you probably treat it very differently, right? I think just in watching my experience, for the most part, people were pretty gentle with the. Okay, Jeremy's laughing because in the 2D version of the experiment, he was a subject once, and he basically just gave it a nice palm and knocked the car over and killed the whole experiment. But other than Jeremy, who does have some anger issues, but people were pretty mellow for the most part. Now, I do think some of it depended on.
You don't have that pretty mellow or whatever in your model.
Well, we kind of do. I mean, you could argue that coasting is kind of the model's version of avoiding that kind of a collision.
They basically.
Well, but it looks to me like they're slowing down as they approach.
Slow down.
That's what I mean by coasting. Yeah. And then it's just coasting on both sides, I guess.
I looked at the dictionary of coasting in German. It means slow it down. It meant walking with little energy.
Right. So the general idea is that what happens in the model is that push-off impulses become smaller and smaller, but as a result of that, your speed begins to trail off. And so you save energy by not actively pushing off as hard, but then you also lose a little time in that process. Yeah, so that's kind of what I mean. Now, obviously, we don't have measurements of anything like that in the experiments, but it's sort of our interpretation that something like that is what's going on.
Thinking about the individual differences, their variability in the evaluation of time, I'm wondering if that variability would decrease a little bit if you were to calculate something like stature or like.
So all the parameters that I'm showing, at least most of the time, are all non-dimensionalized. Not that that necessarily completely takes things like stature out of the equation, but at least hopefully it's controlling for it a little bit. But I think it's possible that you grow up with the body that you have, right, and that kind of informs your experience with the world and how you think about how space interacts with time, and what does it mean to walk to that side of the room in some number of seconds or something. And if you have a longer gait or you have longer legs, that's less steps at least, right? So I don't think it's entirely irrelevant, but hopefully it didn't play too strong of a role in this study, I think.
Yeah, great talk. So there's one conversion. So it's you have one cost function, but of course time is in seconds and then energy is in joules or something. So you could think of both in the same unit if you have some kind of conversion. So what about your time cost in terms of joules? How well does that compare to what you think about resting at a low rate?
Yeah, it's not super far off. I think our time valuation parameters were a little bit lower than like in let's see, not in, yeah, maybe in Elizabeth's experiment. I don't know that you can. I don't know that you can look to the specific numbers and take it too literally. I guess the way in my head, the way I think about it is like when you're sensing energy costs, in the same way that there are the people who believe, okay, you literally have an energy sensor somewhere in the body, versus maybe it's some sort of like vague perception of effort that correlates highly with energy. I think there's probably something very similar when it comes to time, right? So I just don't know how much you can rely on the specific numbers like that to transcend, for example, different tasks or different experiments or different contexts. But yeah, they're not super far off, but yeah. And I think there are some people who would disagree with me, right? Like I think Jeremy is really interested in this. I mean, it'd be cool if you could just see like the same number appear everywhere, but I think the value in it is more in the like less in specific numbers and more in like predictions based off of these trade-offs in general.
The Bornstein paper, I remember hearing about that. Can you tell me, did they measure speed when the people were in that environment, or were these, oh, you're from a big city, come to my lab and walk?
No, I think they went to like streets and just measured with like a stopwatch or something,
right,
people passing by.
Do you think that you would see that same thing if you took the people out of the rural environment or the big city environment, brought them into the same exact setting, you said walk? Do you think, like, is it,
I think that's
behavioral in that regard, or is it completely dictated by the acute environment that you find yourself in?
I think that's a really good question. The obvious answer is I have no clue, but I guess what I would expect is you could find some acute effects. I mean, here's the thing, like this stuff kind of really edges into psychology, right? So much of it is like your perception of things. If you're in a big city and you've never been in a big city before and you're really nervous and you're like, I mean, sure, maybe you might walk a little faster. I don't know. But I think the effect that they're really picking up on, as nicely of a signal as it is, I think it's more something, a learned behavior over time would be my guess. So I feel like maybe if you took someone from the country and then they moved to New York, maybe after a few months you might see an increase in their walking speeds. I don't know. But it's hard to say. I think there's a lot of reasons why these things can all shift around,
And
I think just on Brent's point, I think it's more like if you were to bring city people into the lab and rural people, I think city people would still walk faster in the lab, just out of personal experience, being shorter and walking with taller friends. I'm so used to it by now that like even if I'm walking alone with a new friend who I'm not walking with usually, they'll be like, "Why are you walking so fast?" And I'm just used to
Okay,
catching up.
I'll give you an
with my-
example, and hopefully my wife isn't too mad. She's sitting behind you. I'm a very fast walker in general. I used to be way faster, but she's a slower walker than me. And like, I'm definitely way slower now. I've gotten older, but I think like I've learned kind of over time to walk a little bit closer to her pace, right? And you know, I don't think it's something that happens. Well, okay, maybe it does happen immediately if you're trying to walk with someone, right? But as a learned behavior, even if I'm walking by myself now, I think I'm a little bit slower of a walker than I used to be.
That's what I mean, yeah.
Yeah.
Like if I'm walking by myself, I just walk way faster and with quick steps now because I'm so used to it walking with them.
EFOS used to do. He's not here right now, so I feel bad talking about it. But he's this really funny thing that I thought, and that was he was like I'm a very Northern California, very slow walker.
Mm-hmm.
But he, for some reason, is the slowest walker ever on Earth. But he would do this very interesting thing.
Crowd number?
He would let you go considerably far ahead of him, and then he'd run to catch up with you. And then
I see.
you would just be at steady state, right?
Yeah.
Going away. And he'd run his little legs to catch up with you. And he just that's how he would walk.
Right.
And I'm just wondering what's going on with his.
Well, yeah, I'm pretty sure people have done studies like this, and I do think it's energetically suboptimal to do that. However, I could see there being like a fatigue thing with that, right? If you know, like when you walk really fast for a long period of time, your shins start to burn, right? On the other hand, if you just do a few jaunts, you might expend more energy overall, but it might feel a little bit more pleasant. And this is kind of part of what I mean, right? Like sometimes energy optimality doesn't always quite work, and you know, I think there are perceptions of effort and things like that probably correlate a lot, right?
You could discuss the nose is walk, run, paper.
Right.
So running has a different optimal
Yeah.
speed. The nose showed that.
Oh, that's right. Yeah.
Given a task.
Well, but yeah, the only difference there though is like if you're switching back and forth, then you have like the activation cost every time, right? The transition. Sure, but I think that's when it becomes suboptimal. Right. So what John is referring to is the study by Manoj Srinivasan, where basically he gave people a stopwatch and said, okay, you know, get from here to there in the amount of time on your stopwatch. And so he'd purposely give people speeds that matched a reasonable walking speed or a reasonable running speed, but then he'd give you something in between walking and running, and he'd see what you do. And people didn't walk fast or run slow or something. They didn't choose a constant speed. They'd always do some combination of walking and running. But I don't think they would walk, run, you know, there would probably be one trend that, you know, they'd start walking, realize, oh, I'm not going to make it. And then they'd do a little jog or something.
I wonder if you would see that same behavior if the person was given enough practice and time. Because even when you do these walk to run transition experiments,
yeah,
a lot of times you get somebody to a speed, you go, what do you prefer to do here? And when you're right around their tradition, they're like, I don't really know what I should do.
Mm-hmm.
I don't know. They try to walk a little bit. No, that feels weird. Try to run a little bit. No, that's how you know you're really zoning in on that transition speed.
Right.
And I just wonder if that would always be the case, if this person always had to locomote at like that speed, or if eventually they'd be like, you know, I just prefer to walk really fast here.
Yeah.
I don't know enough about the experiment.
Yeah, I don't know either, but I would tend to expect that people would do the combination thing, but yeah, I don't think they would do it periodically like EFOS.
We are talking about the other here. We think, well, you know, we have a very small village, and he walks very fast. There must be something else that plays a role.
Yeah, well, this is individual time valuation, right? Yeah.
Think about that individual time valuation. I'm not surprised that there were differences between people.
Sure.
Because I suspect under different circumstances, people value time differently.
Right. Sure.
If somebody's trying to get to the bathroom,
Of course.
then
Yeah.
time is valued very differently than just walking across town.
Yeah, and that's a big part of like the point of all this too, right? Is like we can't just say cost of transport minimum. That's what people walk at. It's I mean, we're capturing something, right? But it's so much more nuanced than that. I think people walk at different speeds for all kinds of different reasons.
But it would be interesting to probe the limits of time valuation versus cost valuation.
Do you have an example in mind?
Well, I'm thinking, how much would you have to pay people to
Oh, I
really
see.
blow away the cost?
Yeah, make it explicit.
Yeah.
Yeah, and that is one of the experiments I think we have to do sooner than later is manipulating the time cost specifically. Yeah.
CBD.
CBD. Yeah.
THC. One of those letters.
Well, I always think about
Don't
like
even notice what the time is. And then you get them to walk.
I think about like a foraging task, right? Like maybe you feed someone new pretty images or something, and then the rate of that depends on how fast you're walking, or something like that.
During the winter, you have people walk into the building that's
Yeah.
function temperature.
Right.
Schroeder?
You started with sports, and the NFL draft is too.
It is.
And the way they pick the best players, they do a 40-yard dash, how much money bench press, and so on. And they're always wrong. The best players are Tom Brady goes in the 6th round or whatever.
They're not Anthony Richardson.
Yeah.
Yeah.
And in sports, it's the good players are the ones that are the best at taking away time and space in moving targets. So if you ever look at sports, in hockey, you can ride cost free. Have you ever looked into that data of what those people do and how, you can also become a better scout if you understand.
Right.
Or if you could identify the people that trade off time and cost, because there's also a cost function to everything.
Sure.
Have you ever looked into sports?
So I haven't, but I bring it up for that reason, right? It's definitely like I think a good example of not walking on a treadmill, right? People are it's super dynamic and it's very complex. Now, of course, it's also very explicit, right? A lot of this type of study that we're doing, I would say, is more of like an implicit thing. We don't really want people to think too much about what they should do. Sometimes people ask, oh, should I walk faster or slower? That's like the worst thing you want to hear from a subject, right? You just want them not thinking about it at all, just doing what feels natural. So in sports, it's a little bit different in the sense that usually there's a very explicit goal, right?
There is, but it should come naturally.
Sure. Right. Yeah, no, I think that's exactly the type of thing that like this approach can address, right? And it has that potential to.
Player evaluation.
Right.
Any other questions?
Maybe you speculate what goes wrong with the higher speeds. Is it that your model isn't valid, like the pendulum assumption isn't valid anymore, or do you think it's something else?
Well, it depends if you care if your pendulum holds on to the ground or not. So we could just have a constraint that says, if you're doing that, don't. You're not allowed to. And then it probably would look more like our data.
But humans don't leave the ground. Like,
well, that's why they don't walk at those higher speeds, perhaps. Or if they do, they start to do not an inverted pendulum, right?
Yeah.
And in fact, you were a subject in my study, and you did some of that. Yeah.
So I guess you could say that the pendulum assumption is not valid, or people are not
Yes.
walking that pendulum.
To the extent that people are willing to go at those ridiculous speeds, then yeah, it's not really a pendulum anymore. Yeah.
And do you think your model, you could just get rid of that constraint and make your allow your model to have a 5 phase and do the experiment again?
Like, so you're saying allow running, or you're
Yeah,
saying allow?
Yeah.
I mean, sure is the short answer, right? You're just talking about more and more optimizations, right? So we'd have to have the walking version of everything and the running version of everything, and run both of them over a large range of options and see which is better. Yeah, it's possible. I mean, we could also take like a Rabula type model, which is rather than constraining the point mass to act like an inverted pendulum, you allow for the trajectory to be part of the optimization as well. Usually you do this type of model with 1 or 2 steps. You don't usually do it with many, many, many steps. So it could be a challenge in that sense. It could be very long optimizations, but it's all possible. And I think Osman is working on some stuff a little bit like that.
Any last questions? Okay, well, let's thank Brian.
Thank you.